For example, and today we're going to start with a new chapter, double integers. Find the points on the sphere. Guys, are we good? Yeah? Great. Find the points on the sphere x squared plus y squared plus z squared equals 4 that are the closest from restricted number of the book 3, 1, 1. Okay, so now you have a sphere, and I'm asking you, and now you have a point that does not belong to the sphere. And I'm asking you to find the points that are the closest and the farthest to this point on the sphere. So really, how do I start by formulating the problem? So I need a point on the sphere whose distance to the point 3, 1, minus 1 is the smallest, and I need another point on the sphere, well, definitely another point on the sphere, whose distance is the farthest. What is the distance from 3, 1, minus 1 to a point x, y, z? If I give you a point x, y, z, what is the distance from x, y, z to 3, 1, minus 1? If I give you a point, so x, y, z, here, how do you compute the distance from this point to this point? X minus 3 squared plus y minus 1 squared plus z plus 1 squared, square root, right? We agree? Now I want to maximize this function. Maximize and minimize the square root of x minus 1 squared. Guys, please. Okay. Plus y minus 1 squared plus z plus 1 squared. Subject to what constraint? What is the constraint? Yeah. Want to say something? Oh no? Yeah. Say 3 for x. Oh, x 1 to 3. Thank you. What is the constraint? My x, yes? X squared plus y squared equals 1. Exactly. Thank you. Okay. 9. What is it? 4? 4. Okay. Now, is my function nice? Is it a nice function under the square root? Do you like to differentiate this? It's a pretty bad function. Now notice, if you have a positive function, so if f is a positive function, and you want to maximize and minimize f, this is just equivalent of maximizing and minimizing f squared. The points, you see that? So if f is positive, maximizing and minimizing fx, y, z, even if it's subject to a constraint, is equivalent to what? Maximizing and minimizing. You agree with this? Because the square function is increasing on 0 to infinity. You agree with this or not? Yeah? Now the values of the maximum will change. The value of the maximum will be the square. You see that or not? If I tell you minimize x on the interval 1, 3, where is the point where you reach the minimum? x on the interval 1, 3. Where's the point where I reach the minimum? Yes? See? 1. Where's the point that you reach the maximum? 3. If I tell you minimize x squared on the interval 1, 3, where is the point that you reach the minimum? 1. Where is the point that you reach the maximum? 3. Okay? The maximum will be 9, which is 3 squared, and the minimum will be 1 squared, right? Okay? Of course, the values of the maximum are not the same. Are not necessarily the same because you have 0, 1. Okay? You agree with this? So what is easier? What is an easier problem? An equivalent problem. Is to maximize what problem? Is to maximize and minimize what function? So, anyone? Do that? Square of what? And how do I square that? I remove the square root, right? Do I agree? So an equivalent problem, I mean the answer, the x, y, z answer I get will be the same, but the value of f, x, y, z I have to square it. Do you agree or not? Yeah? We meant maximize, minimize. Okay, so this is let me call this h. Sorry, just so that I don't use f twice. Okay. I'll call it f, x, y, z. It has to be right. Plus y minus 1 squared plus z plus 1 squared, subject to what? Subject to x squared plus y squared plus z squared equals 4. What is that? This is my gxyz, right? Everybody read good? Yeah? Any questions? So this is subject to gxyz equals 4. Okay. What does the theory of Lagrange multiplier tell me? That I need to solve a system where the gradients of f and g are parallel, right? Are scalar multiple of each other. Of course, you can check that the gradient of g is 2x, 2y, 2z. It's never 0 on the surface x squared plus y squared plus x squared, right? We mentioned a condition like that yesterday. You won't have to worry about it, okay? I mean, it will always happen, okay? The gradient of g, what is the gradient of g here? 0 with respect to x is 2x, 2y, 2z, and is different than the 0 vector if x squared plus y squared equals z squared. Anyways, we won't have to worry about this. Okay, so what do I need to solve? I need to solve an equation. The gradient of fxyz is equal to lambda times the gradient of gxyz. Agree or not? Yeah? That's how we set it up yesterday, right? Okay, who can help me with the first equation? Do you want me to write them down, all of them? And what else? What do I need? I need that gxyz is equal to 4, right? Now, how do I set up? What is the derivative of f with respect to x? It's 2 times x minus 3 is equal to what? equal to 2 lambda x. Thank you. Next, someone else? Are we good here or not? Is this first line okay, everybody? Yeah? First line, where does it come from? Fx is lambda gx. Right? Second line, what is this, my second line? Fy is equal to?
Minus 2y minus 1 equals to 2 lambda y.
Oh, so what is it? 2y minus 1 is equal to?
No, negative 2y minus 1.
Okay. This is a plus here.
But we do all that.
Okay.
Yeah.
Very good.
Yeah, and then 2 lambda.
Awesome. Thank you very much. This is just the line Fy is equal to lambda gy. What is well? Third line. 2 times z plus 1 is equal to what? This is just fz is equal to lambda gz. And I have an important equation. X squared plus y squared plus z squared is equal to 4. So far so good? Everybody, so far so good? Now, what do I have to do? Can you express x in terms of lambda? Right, let us solve this. So how do you express x in terms of lambda? So first let me cancel the 2's everywhere. I can do that, right? You agree? I can cancel the 2's everywhere. Do you see that? So what is my x? X in terms of lambda. So I get 1 minus lambda. So minus lambda is equal to times x is equal to what? To 3. Do you agree or not? So bring the lambda there. Boom. Okay, and then what do I get? I get 1 minus lambda y is equal to what? Is equal to 1. And then I get 1 minus lambda z is equal to what? To minus 1. Do you agree or not? Everybody, do you agree? And then I have this x squared plus y squared plus z squared is equal to 4. Now what are you tempted to do? Did I mess something up? Let's see. So you have z minus lambda z, so 1 minus lambda z. That's fine. Okay, now what are you tempted to do? You're tempted to do something. What is it? Isolate xyz. Now, to be able to isolate xyz, what do I need to make sure of? That lambda is not 1. Can lambda be equal to 1? If lambda is 1, what happens here? 0. What happens here? If lambda is 1 and 0 is equal to 3, is that contradiction? And lambda is different than 1. Now can I isolate for x? What is x? What is y? And what is z? Agreed? Everybody, do we agree? Any questions here? Any questions? So far so good? Yeah? Good? Or no? Yeah? What do I have? What is the equation that I need to get? What is one more equation that I have? I have an x squared plus y squared plus z squared is equal to 4. Now what can I plug in? What values of x and y? I can plug them in all in terms of lambda and then find lambda. We agree? So what is that? So it's 9 over 1 minus lambda squared plus 1 over 1 minus lambda squared plus 1 over 1 minus lambda squared is equal to 4. So clear denominators, multiply everything by 1 minus lambda squared, you get 11 is equal to 4 times 1 minus lambda squared. So 11 over 4, let me erase here. Any question? No? So 11 over 4. So what can I say? So 1 so lambda minus 1 is equal to square root of 11 over 2, or lambda minus 1 is minus square root of 11 over 2. Let me add that. So lambda square root of 11 plus 1, so square root of 11 plus 2 over 2, or lambda is that right? Is that right?
Isn't it 1 minus lambda?
1 doesn't matter, right? Because okay. Even if you put 1 minus lambda, you have 1 minus lambda equals this, or 1 minus lambda equals this. It's going to be the same thing. Okay? Great. So what are the values of x, y, and z? What is x? And it's going to be a pretty bad x, I guess. I mean, did I need this? I did not need that. But this is a stupid thing to do, what I did. You realize why? Why? You can just plug in 1 minus lambda, right? You can just plug in 1 minus lambda. You don't need to do everything. Let's see how I'll need it. So what is x minus 1? Okay, but that's fine. You can just plug in 1 minus lambda. So it's a good thing. I did a stupid thing here. So lambda minus 1, or 1 minus lambda, is equal to root 11 over 2, or 1 minus lambda. Okay? So, if 1 minus lambda is equal to root 11 over 2, then what is x equal to? Then x is equal to 3 divided by root 11 over 2, which is 6 over root 11. Y is equal to what? To 1 over 1 minus lambda, so 2 over root 11. And z is equal to minus 1 over root 11 over 2, so it's going to be equal to minus 2 over root 11. Let's just check that when I add them up, what should they give me? 4, right? X squared, what is x squared? 36, right? 36 plus 4, 40. 40 plus 4, 44, right? When you square denominator, you get 11. 44 over 11 is 4, okay? And if 1 minus lambda is equal to minus root 11 over 2, what is x? X will just be minus 6 over root 11. Y will be minus 2 over root 11. And z will be what? 2 over root 11. Yes. Now, how do I find what is the max and what is the min? So I have 2 points. How do I find which is the max and which is the min? What do? I plug them in my function, right? I plug them in my function. So what is this? So I have f of let's see. So f of can you help me? So 6, 2 minus 2. 3, right? I mean, we could technically find the value of x minus 3. I can do the calculations. We can do them again, but there is a way that you can find the value of x minus 3. If you look at the very first system, what is x minus 3? X minus 3 is lambda times x, right? So I mean, you still have to find lambda. We can do that here, or we can just compute it. That's our problem. Let's just compute it. Plus 2 minus, what was it? Is it minus 1? Minus 1 plus minus 2 over root 11 plus 1 here. Plus 1 is 0 here. Here. So what I have here is good. Great. So what do I have? It's 6 minus 3 root 11. Oh, it's going to be a bit fast. 6. The other one. 11 over root 11 squared. Plus 2 minus root 11 squared plus root 11 okay, let's do this here. So 6, you get 36, so everything is over 11 here, so it's 1 over 11. 36, 9 times 11 is 99, right? You agree? Minus 3 times 6, 18, times 2, 36. Plus 4 plus 11, 15, right? Minus 4 root 11. Then 2 plus 11, 4 plus 11 is also 15. Minus 4 root 11. What do you get here? 1 over 11. 36 plus 99 plus 30. So 66 plus 99. So 66 plus 99, what is that? How do you do 66 plus 99? You add 100 and then you remove 1, right? Yeah? 66 plus 99, what is that? 65, right? So it's 36 and 30 is 66, plus 99 is 165, minus 36 I have here, root 11, minus 36 minus 8, what is that? Minus 44. See the rule. Yeah, well then, okay, let me know. So what is the distance at this? I have to compute the other point and I have to compare them, right? Whichever gives the largest value is the largest point, and the farthest point, and whichever gives the smaller value is the. And what is f? F of what? I have minus 6 here. The points are opposite of each other, are negative of each other, right? Is that what I got? Is that what I got? Is this math good? Is this okay? Did you guys see it? Did you guys try it? No? Did you guys try the math? So let's see, what's x minus 3 squared? So it's minus 6. I mean, it should be clear, I think this is the furthest point, right? I think so. So it's minus 6 minus 3 squared plus minus 1 squared, right? Plus 2 root 11 plus 1 squared. So let me do this here quickly. So you're changing the minuses and plus here everywhere. So what do you have? Everything remains the same. So I think you get 36 1 over 11, 165 plus 44 root 11 over 11. Okay? Yeah? You guys see that or not? Okay. Which is the largest? What is the bigger number? Here or here? This one is the bigger number, this one is the smallest number. So the shortest point, the closest point is, what is it? Is this one, it's 6 with 11. The farthest. The book uses the word farthest, so we can say farthest, right? Could be said, right? Yeah. It's not furthest, or both could be said. I think it's both. Both could be said. Okay. Okay, great. Awesome. Enough with Lagrange multipliers. We start a new chapter today, a very important chapter. Integrals, multiple integration. We're going to start by a small motivation. And then you remember our calculus. What's up? Remember our calculus 2 of it. Multiples of it. Okay, so are we all comfortable with the antiderivatives? Yes, sir.
Try to put it numbers. I don't get how multiplying another function by lambda gives you the maximum.
So the maximum will be where the two curves have the same gradient, or have parallel gradients. It's just, there's a proof for it. The proof is very intuitive. The gradient, I mean, the intuition for that is not, at least for me, is not very intuitive. But, so the idea is that, so say you have, let's get back to this. Okay? And how do you draw this function for each value of t, say? You want to solve this, you want to maximize this. So really, if this is equal to 1, you get the hyperbola x equal 1, y equal 1, y equal 1 over x. Now, if t is equal to, so you get y is equal to 2 over x. So you get something like that. Let me just put the axis here. It's going to be way better. And then you do this. Okay? Now we're going to maximize this function subject to, say, gxy is equal to c is equal to k. You need to find the largest value of c such that this is possible. Okay? So this is the curve gxy is equal to c today. And this is, say, the maximum. Now, at the maximum, what cannot happen is that, so you cannot have something like this. Do you agree? Do you agree? This is the largest value of c that you can have. This is smaller. xy, is it? Yeah, I think it's, well, that is. Because, now if you increase it a little bit, like the function cannot increase basically, right? It just has to bounce back, okay? So it's not a very intuitive explanation. The proof is way more intuitive. Well, the proof is way more convincing. So for the proof, we can, we can do it later when we have the tools to do it. Okay, so this is a bit, it's not very, at least to me, it's not very intuitive that you have this tangent. Now, if you want to maximize it just by pictures, the maximum will occur here. It's not an intuitive explanation, and these two must have the same tangent line. Now, if they have the same tangent line, then their normal vectors must be parallel to each other. What's the normal vector in that case? The gradient. So, yeah. It's not something very intuitive. The proof is much more straightforward, actually. Applies the chain rule, boom, immediately, you get it. And it works in 3D as well. So, like this argument in 3D, because the tangent plane must be the same and things like that. Okay, so I don't know if maybe we can do the proof. Maybe we'll do the proof once we finish. Then, I mean, you'll be responsible for it. It's a good proof, actually. It's actually a very quick. Use some polar coordinates. I think I wanted to do it, but now let's worry about this. I mean, on the final you'll have a proof. Okay, so on the final you'll have a proof. Something without numbers, basically. Okay, where you don't plug in numbers. So you'll have one. Okay, that's very safe to assume. Now let's go back for multiple integration. Let's go back to multiple integration. Now let's remember what you did in calculus 2. I think you did this. I think you spent the first few weeks on this in calculus 2. You have a positive function f of x on an interval AB, right? You remember that? So, how did you estimate the area under the curve? What did you do? So you integrated. At the end you integrated, right? That's what you did. The integral of AB f of x dx. How did you estimate it? From sum, yes. You summed over rectangles, right? So what did you say? You picked, I think they do this. So you pick xi is a plus delta x times I, right? For I between 0 and n, right? And delta x is just b minus a over n, right? Is that what you did? So you're taking x1, x2, all of them the same distance from each other, you know, delta x is constant, and you took fxi, and then, excuse my drawing, it's bad, but this is what you did, right? Is that what you did? And you approximated the area from sum I equal 1 to n. What is the area of the first rectangle? It's fx1, right, times delta x. Do you agree? And delta x is constant, so it's fxi times delta xi. You remember this? That's what you did. I mean, delta x is constant, so let's keep it. And then you took n to infinity. Is that what you did? And then you have to use the sum from I equal 1 to n. I is n times n plus 1 over 2, right? You remember this? And then you have to sum from I equal 1 to of I squared. What is that equal to? I can't remember, but you had to use all of these, right? You remember this or no? Yeah, great. So this is it. And then, you know, and I think you define this. I mean, this is not very accurate, but, and you said that this is the integral from AB of f of x dx. Right? This is what you did. Great. Now, I am in 2D, x and y, and I have a function. Z is equal, a surface Z is equal fxy. What does this, so, this is a rectangle here. Above this rectangle, imagine that my surface extends. I have what type of shape? A volume, right? There's a volume, so suppose this is my function. Here, what do I have? A volume. Now the goal is that, estimate the volume under z equal fxy, where fxy is a positive function, above the rectangle. This is all motivation. So we will not do this in class 3 anymore. We will not do the summation business. Under dxy, above a rectangle of the form AB times CD. Okay? Here I had a line segment, AB, and there I will have a rectangle, AB times CD. This is in X, and this is in Y. So let us draw this rectangle at first. And try to do the same thing that we did in Calc. All of this, definitely you have a lot of rigor in these definitions that we won't touch, okay? So if you take any analysis course, analysis 2, you will talk about integrability. What does it mean for a function to be integrable? What is a partition? Things like that. I mean, have you discussed upper and lower sums in class 2 or not really? You have? Okay. You have? Okay. That's good. Now, I have my region in the xy plane, and I have my rectangle AB and CD. Let me follow my notation just so x is up here. Okay. Now that's the same thing that you did there. Partition AB into small subintervals. Okay, so xi into say n subintervals is a plus delta x times I, where delta x is b minus a over n, and I is between 0 and n. So we have here x1 xn minus 1 b. Now do the same thing for the y-axis. So decompose that into yj, which is equal to t plus delta y times j. And what is delta y? It is d minus c over n. J is between 0 and n. Okay? That's what it is, right? It got 2 for each segment separately. Great. Now what can you do? Let's draw these horizontal lines here. And let's draw these vertical lines. I partitioned my rectangles into what? Into smaller rectangles. Not necessarily squared, because C and D and D minus A are not, and M and N might not be the same. But I partitioned it into smaller rectangle. You agree or not? So that's what I have here. So AB times CD is partitioned into rectangles. I call them, I think, Rij. Did I forget? Rij. Xi minus 1 times yi times yj minus 1 and I is from 1 I is from 1 to m, right? To I is m, yeah, and j is from 1. Okay? Are we good here? This is what you do. We're doing doing the same thing as you did in calculus. Now let's draw a small picture here, which may not be very clear. But I have my rectangle here, and I have my surface. So I'm looking at this part of the surface. So it is just above the rectangle. Now, if you pick a point in the rectangle, pick, say, xi star, and rij. Pick one point, say, in this rectangle. What is fxi star? Can I use x? Okay, that's fine. I'll just use x. So delta x, delta y is the area of each of these small rectangles, right? You agree? Now, you have a small rectangle, and you put a point up. So you have a height. Can you represent this as a volume of an object? Isn't it the volume of a box with base this rectangle and height fxi? Yes or no? So say you have a rectangle of area 5, and then you draw a box of height 1. What is the volume of the thing? 5, right? You see that? So I have this rectangle here, and I just go up in height and I close it. What's the volume of this? What's the volume of this? Base, area of the base times the height, right? Because the base is a rectangle. You've seen this? Great. So really, the way to approximate this, to approximate the volume under the surface zfx and above the rectangle, what we're doing here is that we're summing over I and then over j. Well, delta x is I and j. And then as m and n become larger, this approximation becomes better and better. Okay? Of course, this has a lot of rigor involved. We did not discuss everything, and we will not discuss everything. But the idea is that this is how I define the double integral. You know, if you take a limit, of course, this is not rigorous at all. Okay, this is not rigorous. But I mean, even this is really right. I mean, you have a lot of proof to do to get to this result in calculus 2, right? I guess you didn't do the proofs, right? Did you do the proofs? Yeah, sure. We just assume that. Now, here you have to take as m and n goes to infinity. Really, this will be the integral over r fxy dx dy. Or, if you wish, you can call it dA, right? Because the area of each rectangle is delta x times delta y, right? So it's a small element of area. You agree? So here it's a small element of length. Here it's a small element of area, which we'll call dA, right? So delta A is delta x delta y, and dA will kind of be equal to dx dy. Okay? Over the region R. Great. Good. What's even better, double integrals are easy to compute. Let's do a computation of double integrals. So this is more a motivation thing. We won't use it in this course. Okay? I mean, I think in advanced calculus you might do some proofs like that. But anyways. Now, iterated intervals. So if I have fxy over an interval AB, CD, a rectangle x goes from AB and y goes to CD. how do you expect to do this? One of them. Anyways. How do you expect to do this? You know, sometimes I do things that are not okay. How do you expect to do this? Really, your rectangle R how can you say? How can you characterize a rectangle R? It's D, X goes from A to B, and Y goes from C to D. You agree or not? And you're just integrating fxy dx, and then dy. So really, you integrate first over x, and then you integrate the answer over y. All of this, all of this is, at least to me, is non-infinite. That you can, I mean, well, the other intuition is that if you're integrating over the same region, you should get the same answer. But this is not obvious. If f is continuous on AB, and that is called Fubini's theorem. Of course, the continuity business can be weakened a lot. Fubini's theorem. So basically, you can switch the order of integration. This may mean nothing to you, but let us integrate and do some examples. I have an example. I do have an example. Find this integral. Well, doesn't matter. X squared y dy dx. How to compute them? So I want to integrate x squared y dy. So what is the thing that's changing here? The first integral. Do you agree? What is the first thing changing? What is constant and what is changing? Y is changing, x is constant. Great, awesome. So, how do I integrate x squared y from 1 to 2, given x is constant and y is varying? I take an antiderivative of x squared y, keeping x constant. So x squared, y squared over 2, right? And antiderivative of y is y squared over 2. And you evaluate this from y equal 2, y equal 1, and you leave the x, right? Is that clear? Yeah, that's good. I mean, so right here you may need some work in theory, but that's fine. Let's ignore this and let's stay here. I mean, you know, if anyone is thinking to switching to math, you know, you will see like more a nicer type of integrals. Maybe motivated a bit differently, called Riebeck integral. Okay, great. Anyway, so what is that? How do you evaluate this? So you take x squared out. X squared is a constant. Just treat it as a constant. 4 over 2 minus 1 over 2 dx. What do you get here?
3 over 2.
Pardon me?
Can you bring it up?
Yeah, the 3 halves. Sure, yeah. You get 3 halves, 0, 3, x squared dx. What do you get then? X cubed over 3. So 3x squared antiderivative of 3x squared is x cubed. So you get 1 half x cubed. 1 half x cubed from 3 to 0. 1/2 times 3 cubed, which is 27. So 27 over 3. Is that clear or not? Is it clear? Everybody, is it clear? 100%. Yeah. Is it clear how I integrate this stuff? Great. Now if I flip the order of integration, can I help? No? If I flip the order of integration, x will be going from 0 to 3, and y will be going from 1 to 2. What is the answer that I should get? I should get the same answer. Let's try and check this. It's one of the most important theorem in mathematics, Houdini's theorem. So what is it? So I have integrate from 1 to 2, and then I integrate from 0 to 3, x squared y, dx dy. How do I integrate this? So x in the first integral, what is fixed and what is a variable? X is a variable and y is fixed. How do I integrate x squared from 0 to 3? X squared y from 0 to 3 is x cubed over 3, right? Y times x cubed over 3 from 3 to 0, and then I have dy. Now, it's integral from 1 to 2, y times 27 over 3 dy. Agree with this or not? Everybody, do you agree with this integral? Yes or no? Yeah? Any questions? And how do I integrate this? What's an antiderivative of y? It's y squared over 2. So I have 27 over 3 times y squared over 2. From where to where? From 2 to 1. So it's 27 over 3. 4 over 2 minus 3 over 2. Minus 1 over 2. So what do you get? You get 27 over 2. So far so good. Is it clear? Is it good? Let's do a few more just to get let's see, I don't have the time. The time
12 o'clock.
12:05?
12 o'clock.
12, okay, great. So we'll finish today. What you had in mind. We'll move on to harder things. Great. We do more integrals like this? Should we do more integrals? Should we do more examples from the book? I mean, really, this is just going to be okay, so we do 2-3 examples and we call it a day, okay? Just 2-3 examples and that's fine. You know, this is not a course about integration, so I don't want to like start antiderivatives. I mean, we can do a hard one. Let's do a hard one. Integrate over r xy squared. Oh man, I'm afraid of this already. Xy squared over x squared plus 1 dA, where r 0x1 minus 1 3y. Okay, is this a rectangle or not? Is this a rectangle? Is R a rectangle or not? Everybody? Yes. Is R a rectangle? Try to draw R, what do you get? 0, 1, minus 3, 3. Is it a rectangle?
Yes.
Is it a rectangle? Everybody? Yes. Great. So, is this function continuous on R?
Yeah.
Yeah, clearly. So what do you have to do? You just have to decide which you want to integrate first, x or y. Let's integrate x first. So with respect to x, it doesn't really matter. 0, 1, and y goes from where to where? Minus 3 to 3. xy squared over x squared plus 1 dx dy. What do you get here? So y squared is constant, so I can take it out of the integral. Great, I'll worry about it later. And then the derivative of x over x squared plus 1, what's that? This is 1/2 of ln x squared plus 1, right? So I integrate y from minus 3 to 3. And then I have y squared times 1/2 ln x squared plus 1. Doesn't matter if it's an absolute value because x squared plus 1 is always an absolute value, right? It's always a positive number. 1, 0 dy. What do I get here? It's minus 3 to 3. Y squared over 2. Ln of 2 minus ln of 1. Ln of 2 minus ln of 1, what is that? It's ln of 2, right? Because ln of 1 is 0, right? Dy. Now I want to integrate y squared over 2 times ln of 2 on the interval minus 3 to 3. Oops. What's y squared over 2 over ln 2? What's that integral? This is just ln 2 over 2. Y cubed over 3 from 3 to minus 3. This is ln 2 over 2 times 2. 3 cubed over 3 is 9. So I get 8 ln 2, is that right? Sorry, 9 ln 2. Can you please double check? I mean, how can I double check that my answer is good? If I do y first and x first, what should I get? The same. Should we try that? Let's try that. Why do I get the same? By Euclidean theorem. Because my function is continuous on the rectangle. Great, awesome. Did I mess it up? 3 cubed over 3 is 9. So I have, yeah. Great. So how do I start? I start by 0, 1, minus 3, 3, x over x squared plus 1, and then I have y squared, dy dx. So 0, 1, 1/2 over ln x squared plus 1 times y squared here from, oh no. X over x squared plus 1, y cubed over 3 from y is equal to 3 to y equals minus 3 dx. So what do you get here? You get 3 cubed over 3, which is 9. 9 times 9 plus 9 is 18, right? So you get 18 x over x squared plus 1 dx. Now, take a 2 out and leave a 9 upstairs, leave a 9 there. So what you get? You get, this is an antiderivative of 9 ln x squared plus 1 from x equals 1 to x equals 0. So you get 9 ln 2 minus 9 ln 2. Very good answer, right? Are we good? So far so good? Yes? Is it clear? Is it easy?
Yeah.
Yeah, I mean, I can tell you something that to be comfortable, there is a multiple choice on the exam like that. Like, so there are some easy questions that are just giveaways, okay? But there are some tougher questions. But so on the final, there are like questions like this. Yes, sir?
Can you do a problem that's about what we would expect on the final?
Pardon me?
Can you do a problem that's about the difficulty of what we would find on the final for this?
So I think everything I do in class is of the same difficulty than the exam, right?
Okay.
So there is nothing going to be more difficult than what we have seen in class.
Right.
But you just may get a lot more difficult questions, or you may just be overwhelmed.
So more like this one rather than the first one, the first example that we did.
What's the term?
The other one that was.
So I mean I can't remember what.
Yeah.
Maybe it's easier than both. Who knows? But okay. So it's and I think so far I've been very clear on what you'll be examined on, and there are no. You should should expect no surprises. So every question we did, every question that will appear on the final, there is something similar that has appeared in the lectures. Okay, so let's try not to. Yeah. So. Let's do one harder one now. Okay, that's nice. Okay. Good. I think the class is at the same level of difficulty as the midterm. Even the class is a bit harder. Did you guys find this? That the examples in class are a bit harder than the midterm or no? Yeah. I think it's yeah, so the class will always be harder than the exam. 99%. Like if there is something you say, oh, this is harder, sure. But everything you would have seen things like that. Great, let's do a more interesting one. So x is 1 to 3 and y is 1 to 2. X is 1 to 3. So now let's integrate this. So y, the first one, what is variable? What is my variable? Everybody. Y is a variable. What is constant? X. So how do I integrate 1 over a constant plus y? What's the antiderivative for this? It's ln of this something plus y, right? In absolute value. Now, do I have to worry about the absolute value here, or I'm in a positive region? I'm in a positive I'm in a region where 1 plus x plus y is positive. Do you agree? Everybody, do you agree?
Yeah.
Ln 1 plus x plus y from y is equal to 2. Oh man, that's going to be bad. Y is equal to 2 to y is equal to 1 dx. Okay, so if y is equal to, is that good? Differentiate this with respect. How do you get the answer again? Differentiate this with respect to y. You must get this one. Differentiate this with respect to 1. Their with respect to y is 1 over plus a plus y. I'm good. Great, so I get integral from 1 to 3. So it's ln of what? Ln of 3 plus x, right? Minus ln of 2 plus x. Oh, it's going to be bad. Okay. Yes. It's going to be bad. How do you integrate this? What's the antiderivative? An antiderivative of ln of u du? It's u ln of u minus u, right? Do you remember this? U ln u minus u. Integral of ln x dx is x ln x minus x plus c. How do you check your answer is good? Just differentiate the bottom. I mean, you can do it by parts, right? 1 times ln x. Differentiate the bottom. U prime 1 ln x plus 1 over x times x. 1 minus 1, you get ln x. Okay, great. And here's the same thing, right? Is that right? I mean, let's hope I got it right. Is this right? Does this seem right to you? Does this seem right to you? Does the answer seem right to you? Great. So this is just 3 plus x ln 3 plus x minus 3 plus x. Oh my. Let's write it there. So it's 3 plus x ln 3 plus x minus 3 plus x. I'll split the integral now. From x is equal to 3 to x is equal to 1, right? Minus 2 plus x. Let's double check this is good. U prime v minus plus yeah. Is this good? Did you check? This is an antiderivative, right? You saw that? You see that or not? Yeah. Where am I? Here. guess I should not take examples I didn't try before, but that's okay. Great, so 6 ln 6, is there a problem? Minus 6, minus, what is that? 4 ln 4 minus 4, plus 4, minus, where are we here? Minus 5 ln 5 minus 5, minus 3 ln 3 minus 3, right? Is that good? Is that good? Does it look good? Is there a mistake? Or just the integrals are hard to follow? Cos 2. Okay, yes sir.
Isn't it 4 log 4 minus 4? Or?
Minus, you distribute the minus. Okay? Great. You can leave it this way and have fun simplifying. Great. Easy so far? Is it clear now how to integrate stuff? Really, it's everything comes down. Integrating on a rectangle comes down to integrating a one-dimensional figure. Great. Now, check the time. 7, 2, 12, 15. Okay. Now, wait, we can do one more actually. We can do one more. X minus y dy dx. How do you do this? Yes, sir.
Does the same theory hold for like triple and quadruple integrals?
Step by step. Okay?
Okay.
Step by step. So what is x minus y dy dx? How do I integrate this? How do you integrate this? What is variable? So I first go with respect to y. What is constant? What is variable? And what is constant? What is variable? Everybody need more voices? Yeah, and y is? Everybody?
Y is variable.
Y is variable and? Great. Y is not constant, and x is constant. Okay, great. So how do I differentiate x? How do I integrate x minus y with respect to y? 0, 1. So what do I add here? It's just an xy, right? Minus y squared over 2. From y is equal to 2 to y is equal to 0 dx. Technically, this should eliminate all the y's you have. You should not have any y's left after, right? And this makes sense. Great. So what do you get? 0 to 1. 2y minus 2, right? Wait. 2x minus 2, right? And if y is equal to 0, then nothing. So how do you integrate that? 2x minus 2, it's x squared minus 2x from 1 to 0 minus 1. Okay. Is that clear? Everybody, yes sir.
Where did x y come from?
Where did?
X y come from?
You have this function. Integrate with respect to y while keeping x constant. You need to find a function. When you differentiate with respect to y, you get this. What is it?
Ah, okay.
Okay? So say you had 5 minus y dy. How do you integrate the 5? 5y.
Oh my god, yeah.
Okay? Great. Okay, now maybe let's do some properties of the double integral. suppose now, what is the integral on r dA? What do you expect it to be? I have a rectangle here. Okay, let's look at this as volume. I have a rectangle, and you go height 1. You go height 1, and then you close it. What is the volume of this rectangle? The volume is area times the height. What is the height? 1. So what is the volume? What is this integral? Right here you have a 1.
So it's
What is this?
the area.
This is the area of R, right? What is the area of R here? B minus A times D minus C. You see that or not? Yeah? Do you see that? What is the area of this rectangle? AB, A, B, and CD. What is this area? This times this. This is area of R, which is just D minus C times A minus C. Fortunately, B minus A. Fortunately, we can check this. How can I represent my R? This is x from A to B, y from C to D, dx, dy, and then the derivative of 1 with respect to x. How do you integrate this? X from x equal B to x equal A, so it's B minus A. How do you integrate this? It's just B minus A times D minus C, right? Is it clear? Everybody, is it clear?
Yes.
That's easy, right? Are we good here or not? Yes? Integrals, easy. So far so good? Any questions? You want to ask? Ask questions. What you're doing now is just got to, but in a better way, in a more complicated way. Yes, sir.
Have you ever hit the case when you can't switch the x, dy? Like when it's or like when we have to show that that's continuous all the time?
So I will try to avoid giving you the case where Fubini's theorem doesn't hold true. Okay. So again, I said in this course all functions are continuous. Okay. Unless I specifically say that, right? So yeah, maybe I can give you an example on the quiz to try. So what is the integral here? What is the integral here? And see that they don't work. But yeah. Fubini's, the assumptions are weaker. They might be weaker than, anyway, let's not worry about it. So, in this course, everything you'll be able to do Fubini. But, the thing is, sure. On rectangles, you'll always be able to do Fubini. Great. Awesome. Oh, my phone is here. Still have 1 hour left, so we could do things now. Is this stuff clear? Great. I'll try to stay in 2 dimensions now, so that, tomorrow we'll move to 3. Usually I could do some exercises with volumes, but since we're still at the beginning, we'll do things in 2 dimensions. Okay. Okay, so integration. One more thing. One more thing.
Just one.
So I think we convinced ourselves that if we switch the order of integration with x and y, I get the same answer.
Mm-hmm.
You agree?
Yes.
So let's try to work this out here. What did you, is this the first one I did? Oh, it's 1 to 2 and 0 to 3, so here it's 1 x or y, yeah, 1 to 2. And 0 to 3, what was the answer? 27 over 2. Yep. Was that the answer? Great. Now how do I want to show something, I want to try something. Let me just integrate this. And let me times what is this? X cubed over 3 from 0 to 3, what is that? This is 27 over 3, right? Which is 9. And 0 to 3 y dy, it's y squared over 2 from 3 to 0. It's what? It's 3 as, wait, what? X cubed over 3. So 27, oh, this is 1, right? Y squared over 2 from 2 to what? What do you get? Is there something weird? What's weird? If I do each integral separately, and I take the product of these two, I get the same answer. Right? Mm-hmm. What is happening here? Let's do this. So, let's start with a theorem that may help us. If hxy is equal to f of y times g of x, or let's write fxy is equal to h of y times g of x, and where h is continuous on PD and g is continuous on AB, the integral this is dy dx. What is that equal to? Condition. H squared dy dx. This is equal to what? To the integral from c to d hy dy, and from a to b dx dx. Should we prove this, or it's quick to see? Yeah.
Okay.
Should we prove it?
Yes.
Let's prove it easily. So, of course, the integral from a to b, c to d, what is that? G of y, was that right? H of y, g of x. No, dy dx. What is that? How do I integrate this? What is constant here? G of x is constant. Great. So I can take the g of x out, do you agree? I can take it outside the integral. And I integrate hy dy on the top. Agree or not? Yes or no so far? Is that clear? Everybody, is that clear? Now, AB, HY, DY, what type is that? What is this? It's a number, right? You agree? It doesn't depend on x, it depends on x. No, it's a number. So what can you do with a number and the integral? You can take it outside. Alright, good. Whoop, oops, TD. Let's take it outside. And then boom. Okay. I took it outside. I'm left with dx from AB. So far so good? Let's do an example. So 0, 1, 0, 2, x cubed, let's say dy, dy dx. Are these functions continuous or not? Do I have a rectangle? Is this a product of a function of x and a function of y? So what can I do? I can apply this result. I can integrate them separately. So 0, 1, x cubed dx times what? 0, 3 dy dy. So what do you get? 1/4 over e cubed minus 1. Okay? So far so good? So far so good? Is the integrals are okay? Yeah? Great. Now, are we good here or not? Is it clear so far? Is it clear? Just integrals. Just integrals, like in Calc 2, but we're adding one more variable. Okay? So the first part, derivatives, we added one more variable. Integrals, we added one more variable. Great. Now, so far we have restricted ourselves to a volume above a rectangle, right? But you know, you can have better shapes than rectangles. Well, not better, but you can have other shapes than rectangles. What if you have a triangle? What if you have a, I don't know, what if you have a circle, a disk, right? Instead of a rectangle here, you have a disk. How do you find the volume? How do you define it? Again, we're not going to go a lot into the theory of this, but we're just going to state the results, and the rest is just going to be numerical calculations. Okay? Which is good for you, I guess. And for me, I guess. And for everybody. Yes, you just have to do calculations. So, you may visit an interpretation. So, or a motivation. Suppose you have xy positive above a region D. This is my region D. Is it a rectangle? So all the previous theorems that are nice do not apply. Okay? Now really, how can you define that? How can you define this region? How can you define a double integral above this region? The idea is to embed it in a rectangle. Okay? But can you draw a rectangle that contains D or not? Can you draw a rectangle that contains D? Let's draw this one here. And let's call this R. Okay, that's sweet. The book does that. The book does what we did here. That's nice. No update. Yeah. Okay, so so you embed this in a rectangle. Embed D in a rectangle R. And then how do you define this integral? Now I want a function. This is just interpreted as a value. Okay, so I want a function that has the same integral technically. Okay, this is just how do you define this? This is just the integral over d above d of fxy dA. You embed d in a rectangle R, and you define big F to be equal to fxy if xy belongs to d, and to be equal to 0 if xy belongs to R but not to d. So you have a function that you define everywhere, but it's equal to 0 outside d, and is equal to f inside d. What do you expect the double integral of d? This is just the double integral of big F on R is just this one. Let's do something in on the real line. AB. And I tell you define a function f xy, which is equal to f of x if a x b, and is equal to 0 if b x d. What is the integral of fxy of fx? Sorry, fx. What's the integral from a to c of fxy? What is this integral? Oh my God, fx dx. Why am I too very? What is this integral? How do you do it? You split it from a to b and from b to c. From b to c, what is the value of f? 0. So this is just the integral of ab. And on ab, what is f big F equal to? Okay. Same way here. Again, we won't have to worry a lot about this. This is just, you know, how would you define it technically? Awesome. Now let's draw a nice type of regions. So what are regions that are not rectangles? Some types of regions will be interesting. And this is say f1 of y, and this is f1 of x, and this is f2 of x. So a type of region we'll be interested in is just f1 y. So x goes from a to b, and y goes from right? Have you seen this type of region in Cal 2? You have seen that, right? Or no? 100%. So what is above all? F1 is above F2. How did you describe this in Cal 2? Find the area of the region enclosed by the curves F1, right? F1 of x and F2. 2 of x, and the lines x equals a and x equals b. Isn't that what you did in class 2? Yes.
What is the word below?
Embedded. What below motivation? Embedded.
And what is the word after over, written over a region?
Over a region D. Above a region D.
No, double integration.
Double integral fx y dA is double integral over R. Is that? Where? Here? Oh, over general region. Okay. This one you have seen. You agree or not? Have you seen this region before in class 2? You remember this? Find the area between the curves y is equal to f1 of x and f2 of x from A to B. How did you find the area of this region? You integrated f1 of x minus f2 of x. You remember this formula? Have you seen this? Everybody, have you seen this?
Yes.
Yeah? Area under the curve, area between two curves? Great. Now, if I integrate one on a region, what am I supposed to get? The area of the region, right? You see that? So let me integrate one over this region. What answer should I be able to recover? I should be able to recover this one. You agree or not? So what is this region? How can you characterize this region? Y goes from f1 of x to f2 of x, right? F2 to f1, right? Because and x goes from a to b. You agree or not? You start with y and x. Integrate this. This is 1. So y from f1 to f2. So integral from a to b. f1. Do I get the same answer back? Is it the same answer as the one you see? Okay. Of course here, I mean that's not very too much about this. Of course you cannot put the bounds outside. You cannot put the functions of x outside, right? Clearly, you cannot do that. Right? Because this is not a rectangle. So Fubini's theorem holds only for rectangles. Okay? Here you cannot switch the order of integration. Okay? Great. And you know. How you learn double integrals is just by examples. Take 10-15 examples and look at it. At least that's what works with me. So let's integrate. Let's do some examples from the book to integrate around this region. Should we do some examples? Let's do some examples. Integrate y for x per x1. How do I integrate this? Can you sketch the region first? So y goes from where to where? Y goes from where to where? 0 to square root x, right? Y goes from 0 to square root x. And x goes from where to where? So y is under this curve. But x is bounded from 0 to 4. This is the area I'm integrating over. Yes, sir.
Are we supposed to know where to draw?
Yes, 100%. Yeah.
Once, like, if you're and stuff like that, you like, any ones that are complicated, you think that we wouldn't know?
Just the shape of it. How it's shaped. Like, I'm not good, it's not a here. Yeah. X, y is equal to root x, I think it's clear, right? Cube root, fifth root, things like that, you should be able to. X to the 1 over 5, for example, things like that. Okay? So, how do I integrate this? X is constant. So, y is the only variable. So, it's 1 over x squared plus 1. I can pull it out. And then I integrate y squared over 2 from y is equal to root x to y is equal to 0 dx. What do you get here? So you get integral from 0 to 4 x squared over 2, right? No, sorry, x over 2 dx. What do you then get? So 1 over 4 ln x squared plus 1, thank you. From x equals 4 to x equals 0. So 1 over 4 ln 5. Technically, I mean this double integral, you can embed this one in a rectangle and see that it amounts to this one. Okay? It can easily be done. So you embed this region in a rectangle, embed this region in a rectangle, and just consider by cases for example. I mean, but we don't have to. That's fine. Okay? Let's do more examples. X times y dy dx. Now, how do I integrate that? Can you help me sketch the region? How do I sketch the region? What do I have to draw here? I have to draw the line y is equal to x, and the line y is equal to 0, which is the x-axis, right? Now, y goes from 0 to x. How do I sketch this? So y goes from here to here, right? Everybody, y goes from here to here. And where does x go to? X goes from 0 to pi over 2. We agree that this is the region? Everybody, we agree that this is the region? Y goes from 0 to x, and x goes from 0 to pi over 2. Is that the region? Yeah? Everybody, yes, sir?
Shouldn't it be here like 1 over 4 log 17?
Log 17, 4 squared plus 1, thank you very much. Thanks. Thank you. Great. So, how do I integrate this? X is treated as a constant. What's the antiderivative of sine y is? Minus cosine. Differentiate minus cosine, you get sine, right? 0 pi over 2. Now we're gonna do, I hope you can reach the hard part today. So it's minus cos y. Let's keep the x outside. From y equal x. Oh man, we're gonna have it by parts. No way. Oh. So what do I get? I get integral from 0 pi by 2 of minus x cos x plus, so minus cosine 0, so here is cos x, right, minus 1. So what do we get? We get 0, pi over 2. Oh man. Yeah, so it's minus here, plus 1 x. Who wants to then integral by parts? Do it at home. Should I do it? Or do you want me to finish it? I mean, it's integral by parts. You're not going to integrate by parts. You? No? Have you seen this in Calc 2?
Yeah.
You have definitely have seen this in Calc 2, right? Integral by parts.
UV.
No. Okay. No, 100%. So what is it? Integral of u prime v. It's uv minus v prime integral of v prime u, right? Yes, sir. Refresh the memory of integration by parts. Sure. Just let me make sure I got this correct. Let me make sure I got this correctly. So y is minus x cosine x, that's good, plus x here, plus x from 0 to pi over 2. So let's integrate that. So I will split the integral into 2. Plus x dx. So what is that? This is minus u prime v. So if this is u prime, if cos is u prime, what is u?
Sine.
Minus integral, so from pi over 2 to 0, minus the integral from 0 to pi over 2. Again, u prime v, so v prime u. Plus pi squared over 4. Right? Differentiate x sine x minus sine x, so differentiate minus sine x. So u prime sine x minus sine x, minus x, cos x. There's something wrong here. U prime v is uv, uv minus the integral of u prime v. uv v prime v. So you would just say, yeah, so let's differentiate x sine x minus sine x, so we get sine x minus x cos x. There's something wrong. There should be a sign somewhere. Okay, great. uv is x sine x minus the integral of v prime and the integral of v, which is sine, times u prime. This should be good, no? No, I don't think it is.
It's pi squared over 8.
Here? Sure, yeah. But let's try to get this done. See, integral by parts should not be done by just looking. So it's uv. Oh, what am I saying again? It's good. I should have a plus cosine x, but it doesn't matter, right? X sine x, what's then its derivative? Right? Differentiate this one. Sine x, x cos x, yeah, no, that's good. That's good. Always trust. We think at first. So minus pi over 2 sine pi over 2 is 1. 0 to pi over 2 sine x. What's 0 to pi over 2 sine x? 0 pi over 2 sine x. What is that? 1 minus 1 plus 5 squared over 8. Very good. Is that it? Does that look good? Great. Let's do one more. Like that, and move on. So, is that how you used to do integral by parts, or you used to do something else? Is that how you used to do it?
Yeah.
U, B, U prime, B. That's how you used to do it. Okay. Okay, so maybe, do you want me to write it? So some of you know it as dV and du, u dV minus. But is this fine? This is fine? Great. Okay.
Oh no, I didn't.
Let's do one more. Something with trig. Let's do something with trig. 0 x squared, 0 to 1, closest to. Great. Now, how do I sketch this curve? T goes from 0 to s squared, right? This is the parabola T from 0 to s squared. Y goes from 0 to 1. Now, we're not required to sketch it, but I think it's a good idea to sketch it. So how do I integrate this? Cos s cubed is constant with respect to t. Integrate t from 0 to s squared, what do you get? You get s squared, right? So s squared cos s cubed ds. How do you integrate this? This is sine s cubed over 3, right? Sine s cubed over 3. Sine 1 over 3, right? You agree? So far so good? Yeah? Sine s cubed, differentiate sine s cubed, what do you get? 3s squared over 3 gets s squared cos s cubed, right? Yeah? Great. Now so far, we've considered regions of this form. So y is varying between two functions of x, also b1 and 1, and x is between a and b. These are all the regions we considered, right? And did we do well? Okay, this stuff here is just integrating. Integrating Calc 2 is good. Now, what if we consider regions of this form? So really, x is between two functions of y, and y is between two values. So y is between c and d, and x is between g1y and g2y. Is there anything wrong? It's actually the same thing. Now if you convince yourself and you rotate the thing, you get the same. Right? Just convince yourself. If you look at it this way 50 feet, right? And you call this x and this y, it's going to be the same as before. Have you guys seen this? Yeah? Have you seen this in Calc 2 when you look at the surface of something solid that you rotate? I mean, most of the problems are you just flip x and y. Okay? Most of the formulas you can flip x and y and then you get the formula. Okay, let's do some nice examples. Oh man, that looks like a bad one. Oh no, that's good. So integrate. Let me pick. I want to pick a big number here. 0x1. So how do I sketch this? X goes from where to where? X goes from where to where? Everybody? From 0 to y. So you draw the line x equal y. And x goes from 0 to y. And y goes from 0 to 1. This is your region. Do you agree? X goes from 0 to y. This is the line x equal y. X goes from here to here, and y goes from 0 to 1. You agree with this draw? With this sketch? You sketch region like that in Calc 2 when you found the area and the surface, no? When you rotate around an axis. Did you do that or not? You didn't do that in Calc 2? You did. 100% you did. This is, you spent like a month on this. Rotate around an axis and draw the region and yeah. Great. How do I integrate this one? Is x a constant or not? In the first integral, x is not a constant. But what is a constant? Y. So e of minus y squared is a constant. I can treat it as a constant. So when I integrate that, what do I have? So you have to integrate 1 from 0 to y. What do you get? Y. E of minus y squared 0. Oh man, that's sweet. Can I integrate this thing? How do I integrate this thing? It's just e of minus y squared over minus 2 from 1 to 0, right? Let's see. Differentiate minus 2y over minus 2, you get y. Very good. So you get minus 1 half e of minus 1 minus 1. And that's good, right? You guys see this? Is that how you did this like that, right? Yeah? Is it clear? Everybody, is it clear? Integrals are good? Yes, sir.
What are you drawing?
I'm drawing this region.
And where is the function?
Pardon me?
So,
I'm just sketching it, just for you to see. You don't need to sketch it.
we don't draw exponential.
Pardon me?
Exponential.
No, I'm drawing the region, not the function. X is from 0 to y, right? X is from 0 to y, and y is from 0 to 1. That's my region. Right? Now, let's draw one more. Let's do one more like that. Let's see. Okay, I have one, but it may be bad actually, so let's try it. Oh no, that's not the one I want. Okay, let's do it. I hope it's not. I'll switch it a bit. So the integral x is from 0 to y. X is from 0 to y, and y is from 0 to 2. And then what do I have? I have x square root x squared minus y squared dx dy. How do you sketch the region of integration? So x, so what line do I have to draw? The line x equal y, which is here. Great. And then, so x is from 0 to y, so I'm here. And y is from 0 to 2. Right? Are we good? Is sketching this okay? Great. So how do I integrate this? Oh man. Let's see. That's to be integrated, right? So you have the square root of x squared times the root of x squared. right? So how do we integrate this? So from 0 to 2, so it's just x squared minus y squared to the 3 halves over 3 halves times 1 half dy from x is equal to y and x is equal to 0 is that so it should be y squared. Sorry. Yeah. No, that's something. Y is from 0 to 2. Yeah. It should be y squared minus x squared. Yeah, because in the book it's x squared minus y squared, but I flipped them. So let's do this. Sorry about that. The region is still the same. How do you integrate that? So this is y squared minus x squared to the 3 halves, right? Over 3 halves minus 1 half. Is that right? From x equals y to x equals 0. Is that right? Is that right? Differentiate, bring the 3 halves down. You cancel out. 3 halves minus 1 is y squared minus x squared to the 1 half. And differentiate minus 2x. You get differentiate minus x squared. You get minus 2x divided by minus 1 half is 1. Right? 0 to 2 dy. So what do you get? Integral from 0 to 2. This is 0, right? And then you get minus y squared. So it becomes plus with this one. So you get 1 half y squared to 3 halves over 3 halves dy. So you get integral of y cubed over 3. What is the integral of y cubed over 3? It's y4 over 12 from 0 to 2, right? So y4 over 12 from 2 to 0. So 16 over 12, what is that? This is 4/3, right? Are we good here? Is there anything unclear in the integration? Is it clear or not? And what you can do, you can say u is y squared minus x squared. You used to do this. U is y squared minus x squared. Du is blah blah blah, and then right. But now it's you don't. Yes, sir.
Which graph is out of this equation?
Pardon me?
Which graph is referring to this question?
Which?
Which graph?
Oh, this is just the region of integration. Okay, I'm not graphing this function. I'm graphing the region. Okay, so what time is it? Maybe we can do one more example. Oh, 20 minutes. Okay, so we can move to something new actually. That's good. This is just straightforward integration. Okay? Any questions on this? Do we integrate? Now usually, so the vibe that I get from the class that people are confused, but your exam said that you're actually not, so it's, yeah, anyways. Are we confused with this? Is it clear?
Yeah.
Yeah, actually. Great. I mean, it took me like 5 hours to understand this when I was there, but this is good. Okay. Are we good? We all know how to integrate business. This is easy. Yes? You gave me an idea, thank you. No, I'm kidding. Trick stuff, no. Not to my memory, not to my memory. And partial fractions. Partial fractions, I mean, they're not too complicated, right? I mean, if you do the long way, they are complicated, but you should be able to spot how to do it. No? Did you learn this way? No? You spot how to do this, right? You don't put A, B, and C. So if I give you a partial fraction, you should be able to spot it immediately. Like if I tell you write this partial fraction. What is this? Immediately partial fractions. So you write the one as x plus 6 minus x plus 5, right? And then you get this. Right? You guys, yeah? So yeah, you might get things like that. Great. Now, let's try to do an integral. Now this is important. You will get a question like that on your exam. So it's important that you listen. Okay? It's very important that you, and really all of those examples are just to lead this one. Here we call it switching the order of integration. I mean, now I'm kind of jumping between sections so that I do the easy stuff first in every section, and then we'll go to the harder part tomorrow. Okay? Great. 100% yes. Okay. Let's do an integral. If I ever ask you to evaluate this integral. What do you need to do first? What did we do at first when you saw this integral? What did we first do? We sketched the region of integration. How do you sketch the region of integration? So you have to draw the line x equals 3y. What is the line x equals 3y? So y is equal to x over 3, right? X equals 3y is y equal 1 over 3x. So it's here. This is the line x equals 3y. And then what is the line here? Y goes from 0 to 1. So y goes from 0 to 1. And x, and x goes from 0 to 3. So if y is equal to 1, what is the value of x here? Everybody, if y is equal to 1, what is the value of x? 3. Wait a minute, you get your 3 here, right? Now, I want x to go from 3y to 3. What part do I sketch? This one or this one? X goes from 3y to 3. X goes from 3y to 3. Here or here? 2 or 1? 2, right? X goes from 3y to 3. You agree? And y goes from 0 to 1. That's my region. Everybody, do we agree with this?
Yes.
Do we agree? Yeah? Any questions on this? Do we agree? Now I tell you, I ask you to integrate this one. What happens? Any questions on this? Is it clear? Don't hesitate. If it's not clear, just say. Okay? Questions? You're good? Yes, sir.
How comes the bottom square out?
Very good, thank you. X goes from 3y to 3. What is bigger? X equals 3y or x equals 3? In x direction. In the x direction, what is bigger? 3, right? 3y is smaller. So put a number here. What is the value of y here? 0. So x is 0 and y is 0. So 0 is smaller than 3. Put the value here. Say y is 1/4. So x is 3/4, right? It's smaller than 3. Okay? Is that clear? Okay, now I'm asking you to integrate this. What happens here? What happens here? Can you integrate the x cubed? No, it's a bit difficult. Right? Ex cubed is a bit hard to find. Now, fortunately, see that? Don't, okay? Fortunately, there is something that you can do. So here I said that x goes from 3y to 3, and y varies from 0 to 1. You agree?
Yeah.
Y varies from 0 to 1, and x varies from 3y to 3. Can you describe it differently? Can you bound x between two constants and y between two functions of x? What are the two constants you can bound x with? X with, yes? X goes from 0 to 3. And what are the two functions of x where y varies? 0 to 1 over 3x. You agree or not? If you don't agree, let's convince ourselves by drawing this. X goes from 0 to 3, right? And y goes from 0, this is x over 3, and y goes from 0 to x over 3. This is the line, y is equal to x over 3. This is my region. Here I'm just describing it vertically, and here I'm describing it how? Horizontally. But it's the same region. You guys see this? So when I integrate this function over this region, would it matter what way do I use? Or it should be the same answer? Should be the same answer. Great. Do we see this? Okay. Now, so let's flip the order of integration. X goes from 0 to 3, and y goes from where to where, did we say? From 0 to x over 3, ex cubed. No, there is something not right.
Is it ex squared?
X squared, yeah. It's squared, right?
Yeah.
Yeah, but I said cubed at the beginning. Did I say ex cubed?
I think squared. I have
Right.
ex squared.
Ex squared. I mean, I said ex cubed you cannot integrate it, but ex squared is the same. You cannot integrate it, right? dy. Now, can I integrate this?
Yes.
How do I integrate this? Ex squared is what? With respect to y is? Constant. So I can take it outside. Integral from 0 to 1. I have ex squared. Now, what is the integral of y from 0 to x over 3? dy 0 to x over 3. What is that integral? X over 3. We see that or not? Yes. 0 to 3. 0 to 3. Thank you. Integrate y from 0 to x over 3. What do you get? Integrate this function, ex squared from 0 to x over 3. Ex squared is a constant. What do you get? You get x over 3 times the x squared. You agree or not? Everybody. X over 3 dx. What's the next derivative of this? It's just ex squared over what? 6, right? 3 to 0. What is that? This is e9 minus 1 over 6. Is it clear? Is it clear? Let's do one more. See? There are lots of examples. So let's do that. 0, 1, root x1. No, here. All of these are from the book. dy dx. So what's the first thing that I do? The first thing that you can try is, I would recommend drawing first. But here, can you evaluate this integral? Just to check. Can you evaluate this antiderivative? Root of y cubed plus 1. You may not be able to. Right? Even with that trick stuff, I don't know. Anyways. But this is not the goal. What do I do next? I sketch. Let's sketch this. So what are the curves that I need? I need y is equal to root x, and y is equal to 1. This is y is equal to root x, and y is equal to 1. And x varies from 0 to, x varies from where? 0 to 1. So what is my x? If y is equal to root x, if y is equal to 1, what is x equal to? 1. Agreed? Now, what is my region? 2 or 1? Y is above root x and below 1, while x is between 0 and 1. Where is my region? This one or this one? Does this one raise your hand? Why? If it's this one or this one? Y is above root x and below than 1. This one or this one? First one. It's above root x and smaller than 1. Y x is from 0 to 1. This is my region. Now sadly, you cannot integrate this. I need to describe x between two functions of y, right? X between two functions of y, and y between two constants. What are my two constants here for y?
0 and 1.
0 and 1, very good. So y goes from 0 to 1. And my x value and my x between what two functions of y? Look at it this way. X goes from where to where? 0 to
X squared.
0 to. So I want x in terms of y.
X squared.
X is equal to y squared. X goes from 0 to y squared. Square root. Oh, wait a minute. You can integrate this, right? Now you can integrate this. Square root of y cubed plus 1 is constant with respect to x. You integrate that, you get y squared to square root y cubed plus 1 from 0 to 1. Okay? You will have a question like that on the final. Okay, just to be very clear, you will have to do this.
Long answer or short answer?
You will see the power. But you can expect both. This is a good multiple choice, for example.
Okay.
Okay? And it's a good long answer.
Okay.
Both are good.
Okay.
So how do you integrate this? How do you integrate this? So y cubed plus 1 to those 3 halves, right? Divided by 3 halves, and then you have 3y squared, and so you divide by 3 from 1 to 0. What do you get? So it's 2 over 9, right? 2 over 9, is that correct? 2 over 9. 2 over 9 times 2 to 3 halves minus 1. We have time for one more or not? 5 minutes? Yeah, we have time. Let's do a harder one. Let's pick a harder one. Okay, that's a good one. It's such a good one that I need to. Arc sine y, pi over 2, and 0, 1. Okay. Now, can you integrate this business? Cos x square root of 1 plus cos squared x. I mean, I'm afraid of it. I would be afraid of it. I mean, even like the derivative of cos squared. What is the derivative of cos squared? It's 2 cos times minus sin. Sadly, it's bad, right? So really, you can't integrate that. Now, what do you have to do? What do we do then? We sketch the region. So x goes from arc sine y to pi over 2, and y goes from 0 to 1. We all agree that it's easy to sketch the y,
Yeah.
right? And it's easy to sketch x equal pi over 2, right? X equal pi over 2, this last. Now, how do I sketch x equal arc sine y? There are many ways of doing it.
Isn't it like the U's?
Isn't it?
There are like a bunch of U's going back and forth.
Sure. Yeah. I mean, if x is equal arc sine y, and say x is positive, right? Y is positive here.
Y equals
So
sine x.
y is from 0 to 1. So what is y equal to?
Sine
y is sine x. Sine x is 1.
Yeah.
So can you sketch y equals sine x?
Yes.
Can you sketch that?
Mm-hmm.
Y is equal to sine x, how do you sketch it? Right? It says pi over 2 means this. No, it's not this, I think this, right? Yeah?
Mm-hmm.
This is the line x equals arc sine y. And y is between 0 and 1. And x is between arc sine y and 0 pi over 2. Now what's arc sine of pi over, if x is equal to pi over 2, if x is equal to pi over 2, what's the value of y? If x is equal to pi over 2, what is the number that gives you arc sine y is equal to pi over 2 is? 1. Okay, it's always safe to check that the bounds are good. I'll give you this, but you should be able to double check this. Great. X goes from arc sine y to pi over 2. I have two regions, and while y goes from 0 to 1. Is it here or here? X goes from arc sine y to pi by 2. So x goes from the smallest, which is arc sine y, to pi over 2. Or here, 0, which one? This one or this one? 1 or 2? Everybody? Everybody? What is the region? 1 or 2? 2, right? Because x goes from arc sine y to pi over 2. Now I describe it in terms of y between two constants and x between two functions of y. How do I describe it? Y between two functions of x and x between two constants. What are my constants here? X goes from where to where? X goes from 0 to pi over 2. And where does y go to? Y goes to from 0 to, what is this curve in terms of x? X is equal to arc sine y. How do you solve for y? Y is sine x because there are intervals 0 pi over 2. So 0 y sine x. Oh wait a minute, that could be done here. So let me do this integral, let me finish this. Zero to 1, what did we say? X goes from 0 to pi over 2. And y goes from 0 to sine x. What did I have here? Cos x square root dy dx. Great. So let's integrate that. So when I integrate, this is a constant with respect to y. When I integrate from 0 to sine x y, what do I get? I get sine x here. So I have this 0 to pi over 2 sine x cos x square root of 1 plus cos squared x dx. Now what's the derivative of cos squared x? This is minus 2 sine x cos x, right? Derivative of cos squared x is minus 2 cos x sine x. Wait a minute, I have this derivative here. Sine x cos x, I can relate to the derivative of cos x squared. So what do I get? I get 1 plus cos squared x is 3 halves, right? Over 3 halves. And I have to divide by minus 2. From pi over 2 to 0. What is that equal to? This is, so the minus 2 will cancel out, so you have minus 1 over 3. 1 plus cos squared pi over 2. What's cos squared pi over 2? This is 0, so you get 1. Right? Minus 1 minus 1 plus 1, which is 2 to the 3 halves. So what do you get? You get 2 to the 3 halves minus 1 over 2. Okay? Is the derivative clear? Are the derivatives clear how I take the integral? Yeah? I mean, so you could do this. You can say u is cos squared and then do the u. But since it's... Anyways, great.